Hi, in this video we're going to look at finding the area of an enclosed bipolar curve. Now this is part of a book, so this link I will put in the notes of the video, plus also the actual link for the actual GeoGebra app. Okay, I've already got it open here. Okay, so here we've got the polar equation r is equal to 1 plus cos theta. And I want to find this red shaded area. This is from alpha is equal to 0 to beta is equal to pi. Okay, how am I going to do that? Okay, so what we're going to look at this one is the actual proof. Okay, so what I'm going to do is I'm going to pick a point on here. Okay, and you'll see it now, and draw in. So I'm going to pick this point here, and you can change the point by using the slider. Okay, where the angle from here to here is theta, and this is p. This I'm going to call a little bit of theta, and this I'm going to call p dashed. Okay, then what I'm going to do, I'm going to create another sector where this is point Q, and this is Q dashed. Okay, and the area, the actual area is somewhere between the area of that, for this particular part of the curve, area of the yellow one is somewhere between the area of the yellow one and the area of the green sector, and I'm going to call that a little bit of A. We're going to use the idea delta A. Okay, how are we going to do that? Well, if I'm going to click and talk you through the proof here. Okay, so the area, the little bit of area there, is bigger than the area of the sector P dashed, but less than the area of sector Q dashed. Okay, so the area of P is going to be a half r squared delta theta, this angle here. Now, this angle has to be measured in radians, otherwise this is not the area of a sector. Okay, and then the area of the green sector is going to be, well, okay, so here we have radius r. So sorry, from here to here we have radius r. That means from here to here we have radius r. And then I'm going to make this little bit of extra bit called delta r. And therefore the area here, this length here is r plus delta r, and therefore the area of the green sector is a half of r plus delta r squared delta theta. Now, if we let delta theta be equal to 0, and delta r will then be equal to 0, and then a half of r plus delta r squared will be in fact a half r squared. Now, I'm just going to do that by showing you here, and here you can see the actual areas. And what you can see is they are actually getting closer and closer to each other as we make this smaller and smaller. Okay, that's about small. There we go. We made it really, really small there. In fact, we've actually got the same area there to 2 decimal places. So if we squeeze it between these two things, that means that delta A will approximate to a half of r squared delta theta, and then if we divide by delta theta, we're going to get delta A over delta theta is equal to a half r squared. But as delta theta goes to 0, delta A over delta theta actually becomes dA over d theta. If we take limits as delta theta goes to 0, that's the definition of a derivative. And therefore, if I got the derivative and I want to find the area, then I need to integrate the function a half r squared delta theta. And as I was interested in finding the area from alpha to beta, then I'd need to make the limits alpha to beta. Okay, and I can click here, and actually it will give me the actual shaded area, which is 3 pi over 4. Okay, now, so this is how this works. So again, you can change these values here if you want to on the app. You can also move these around a bit as well if you want to. Okay, obviously when you make delta theta equal to 0, you have an infinite number of these sectors. Okay, I hope you've understood, and like I said, the actual app will be in the notes of the video and the link to the GeoGebra book where you can see all the apps for this particular topic. I hope you've understood, and I thank you very much for watching.